And our final paper is going to be by Bob Buckheim, spectroscopic observations of the 2024 eclipse of V695 Cyg.
Yeah, that's one of John Stone's. Well, no, it's made after he sold the company. Thank you. Okay, this is the obligatory picture of my backyard observatory. This is an interim report because there are a few things here that are not completely baked, but I felt like this was a good opportunity to get some questions and ideas and maybe course corrections if necessary. I found out about this project because of an AAVSO alert notice that came out in, I think, late February, mid-February, calling for photometry and spectroscopy of this star, 695 Cyg, and asking to particularly focus on the blue end of the spectra, the calcium H and K lines. And that seemed like a perfect opportunity to put my new UVEX spectrograph into service since it's been optimized for near ultraviolet down to the Balmer jump. So all the spectra that I'm going to show come from, save one, will come from my UVEX on a 16-inch RC using the standard 600 line per millimeter grading and the standard 23 micron slit, which gives a resolution of about 1200 in the wavelength range that I'm measuring in, which conveniently is a perfect match to the Johnson B band photometry. Oops, can I go backwards? Thank you. You remember that first picture that Menke showed of AZ Cass with the big red star? He's got better graphics than I do because the two systems, I realized when I was watching his talk, are almost cousins of each other. Remember AZ Cass, big red giant star and a little main sequence blue star. His was in a 9.3 year orbit. V695 Cyg is a main sequence B3 star in a 10.3 year orbit around a red supergiant, spectral type K41b. So the action that started earlier this year is there's that little blue main sequence star, which, by the way, not to scale. If I drew this to scale, that little blue star would be about 1/3 the size that I've drawn it. Early in the year, the action started with the blue star passing behind the red star. Takes a few days for it to completely disappear. It's kind of partially occulted for at least a couple of days. Then 2 months occulted by the red star before it comes out the other side and then continues on its long orbit around the red supergiant. And when I say it goes behind the supergiant, it's way behind because it's a 10-year orbit. The eclipse is seen nicely in AAVSO photometry, shown here in 3 colors. Observer Wolfgang Wollmann in Austria used a DSLR to measure the drop in tricolor green. So you can see I'm covering about 2.5 months from just before first contact to sometime after fourth contact. Wolfgang also used tricolor B since he had it available. And you can see the eclipse depth is nearly twice as big, about 2/10 of a magnitude in tricolor B. And Gary Walker was using photometric Johnson-Cousins B band, where the magnitude drop is close to half a magnitude, all of which makes sense because it's the blue main sequence B star that's disappearing. So the bluer your spectral region, the greater the magnitude drop. And the triangles along the bottom are nights where I took spectra of the system. And here's a flux calibrated spectrum. The first night that I was on it was just before first contact. Let me get this right. Oh, for the record, I used the B-band photometry to flux calibrate the spectra using the David Boyd method that he described here several years ago. So this is a time series spectrum now from a few days before disappearance of the blue star. Here's the first night. Here's a spectrum showing both stars still visible. And I've highlighted H, gamma, delta, calcium, K and H, and H zeta there, so you can kind of get oriented. Spectral range goes from 3,650 angstroms to 4,600. So 2 nights later, the blue star is starting to get covered up by the red star. So the blue end, his intensity has dropped quite a bit. And out at the red end over on the right, not much change. 2 more nights, and the blue star is practically gone. So the spectrum is changing dramatically on the left side of the curve. And 2 more nights, and the blue star is completely gone. So you can see what's happening, and you see some curious changes down there, particularly in the calcium K and H region, which we will come back to. So the photometry shows the eclipse, the spectroscopy shows the eclipse pretty much the way you expect them to. But I was frankly kind of worried about the deep absorption feature at calcium K. So here's a sanity check on what you expect that spectrum to look like. I made went and found an isolated main sequence B3 star, made a spectrum of it, flux calibrated it to the magnitude of the B star in V695 Cyg. So that's what you expect to see from if you could get the blue star in 695 Cyg all alone. Then found a K3 supergiant, did the same thing, flux calibrated it to the brightness of the supergiant here in this system. And that pink line is the red supergiant spectrum. Added them together. The sum of those two is what you expect to see looking at V695 Cyg out of eclipse, which is shown in the gold line. That's a pretty good match. So I thought, pretty good, except look at that calcium K line. In the gold, there's this huge dip. It's not coming from the supergiant. It's not coming from the B-type main sequence star. So this is the first hint that I was seeing what Dr. Bennett, who issued the alert, was looking for. The chromosphere of that red supergiant. So I've zoomed in. Do I have another slide there that does that? Yeah, you can see the details zoom in there on the calcium K in particular. The difference between the observed and the black line is the calculated expected spectrum. So what's going on here? If you move up and look down on top of this system, you've got the red supergiant there in the middle. Earth is off to the right. The red supergiant is surrounded by chromosphere, probably an extended atmosphere, probably a wind. There's the blue star in its orbit going around, mapped not to scale, obviously. So, and it's shown here just reappearing after fourth contact at the end of the eclipse. And so the light that comes from the blue star to us passes through the deepest layers of the atmosphere of that supergiant star. couple of nights later, the blue star has moved on in its orbit, and now the light coming to us passes through a higher, more tenuous layer of that chromosphere or atmosphere. You know, another couple of nights, another. So we're using that blue star as a probe of the extended atmosphere of the supergiant star. And you can see it happening in a series of spectra taken during this part of the eclipse. That on the top is the full spectral range from 3650 to 4200 angstroms. And the inset in the lower left is zoomed in on the calcium K line, which turns out to show kind of the most dramatic effects. So this is the night after the blue star reappeared. So we're skimming right through the densest part of the supergiant's atmosphere. 2 nights later, you see in the calcium K detail, the blue curve, less absorption, we're higher in the atmosphere. 2 nights more, same effect is happening. So you can see as we pass through the higher layers of the atmosphere, there's less absorption, it's a little more transparent. And once you see what's happening in the calcium K line, you see it happening all over the spectrum. There's all these little bumps and wiggles, and they're all kind of moving up and getting smoothed out as time goes on. Well, now this is where I step sufficiently far out of my area of expertise that, as Tom Kay once said, what I'm about to tell you might be completely wrong. But Eaton and Bell wrote a nice paper about their observations of the 1992 eclipse of this system. And they had a really clever way of translating the spectra into a concept of what that transmission through the atmosphere is. And the key is this equation. The spectrum we observe is equal to the spectrum of the K4 supergiant, because we see it, plus that main sequence B star spectrum, but modified by the transmission of the stellar atmosphere that its light comes through its way to us. And we have enough information to solve that equation for the transmission function of the chromosphere. Shown here, we know what we observed, and we know the spectrum of the K4 supergiant alone because I made spectra while the blue star was occulted behind it. And I have that spectrum that I made of a isolated B3 star properly flux calibrated. So I can solve this equation. And here's the result for the first night that the blue star appeared. The identification of the features on the top trace are a little conjectural, but they match species that Eaton and Bell and others claim to have observed in prior eclipses. So this is no longer the spectrum of the star. It's the transmission spectrum of the atmospheric path through that chromosphere star. So this is the night the blue star first appeared. The next night, transmission looks like it. Everything went up. Next night after that, same deal, getting more tenuous, more transparent. Several nights after that, exactly what you expect to see, which impressed the living daylights out of me that none of this is a new discovery. It was measured at Mount Wilson in I think the 1950 eclipse. It was measured at Dominion Astrophysical in the 50s and 60s and 70s. But the idea that I can do in my backyard relatively easily what they struggled to do back then is, to me, darn impressive. And seeing the transmission function through the atmosphere of a star, I find just mind-boggling. But there is one grave caveat, however, and that is I have relatively low resolution, R of 1200. Here's a comparison of my spectrum in black with a spectrum taken by Gerard Persha in New Mexico on the same night with his R of 7700, so about 6 times better resolution. And you can see here, everything I'm seeing is a blend of the incredibly dense and complicated spectrum of that supergiant star. So that's a caveat, but nevertheless, it remains to be seen if there's actually any scientific value to what I've done, but it was definitely worth getting up at 1 o'clock every morning in order to take an hour of spectrum of this guy to be able to see all this happening. Definitely seeing changes in the spectrum. I think I know what I'm seeing. A tantalizing view of the supergiant's chromosphere and wind. Alas, I may not be around for the next eclipse in 2034, but I'm counting on somebody out there doing a repeat of this with higher resolution. More importantly is, if this sparks your interest, Dr. Menke, a very similar event is going to happen on a star right next door, 32 Cyg, next March, a kind of a grazing eclipse through the atmosphere of 32 Cyg. So where'd John go? Higher resolution, longer span of spectral range, be perfect for this. And 695 Cyg is like a 3rd magnitude star, and 32 Cyg is maybe 4th magnitude. You can see them both with your naked eye. So you got a lot of signal coming in. You can use a smaller slit. You can get higher resolution and take a new set of data. Thanks to Wolfgang and Gary and AAVSO and Simbad and ADS. That concludes my report, I think.
There's more juice in there, Bob. There's more juice in that data.
I don't doubt that. And that's one of the things that's not fully baked is I've got a lot of analysis to do.
Now you can actually model the rate at which the density of the atmosphere decreases and project out where its effective limit is. And then using that other spectra, the high density spectra, scaling it with your stuff, now you get to look for the elemental abundances in that thing. You got lots of work ahead.
Yeah, great minds. There is a paper describing how to take that linear path, that covers, of course, all altitudes, and translate it into a radial path. And the conclusion of that paper was, you have to make so many assumptions, like the assumption that it is only a radial density gradient, which are demonstrably not true. I couldn't see it, maybe because it wasn't happening, but probably because of low resolution. There are observations from DAO and Mount Wilson that are best interpreted as giant convective bubbles coming off of that supergiant and making their way through the atmosphere right here, but not over here. It's a really dynamic but subtle part of the universe.
Yeah, so Bob, if you like this, I believe V695 Cyg is part of a group of stars called Zeta Auriges.
Yeah,
Uh,
read the book.
Yep. With that, and they are the only type of star system where you can actually study the chromosphere of a star other than our own sun. So they're
Yeah,
really cool. And these eclipses, there's maybe 15 or so Zeta Auriges known. And so, lots of good studying that can be done.
yeah. And the book is fascinating, and the extended articles in the observatory by Dr. Griffin are really wonderful histories of success and failure in measuring these stars.
Okay, Bob, I'm not sure how to answer you. I wish I had seen your talk earlier. I have to go back and look at my own data to see if I get the same kind of stuff that you did. That's point one. And I congratulate you on your talk, especially on your final graphics, which are much fancier than I had. Second thing, though, is I don't know what it's like to work with a magnitude 5, I think yours is, compared to 9 and 11 for the 2 stars in my system. It's a huge difference in having to take a couple of hours to get a fairly crummy spectrum. But anyway, I certainly applaud what you've done, and I don't know why you wouldn't keep on working.
No, I'm worried about keeping on breathing.
You think I have that worry? I have that worry too, including about the 2027 eclipse.
Yeah. Regarding Bright Star, there are peculiar issues. I had been using a CCD on my Alpi, so I had 16-bit camera and everything. The CMOS camera that I have on my UVEX is a 12-bit camera. And so at the red end of the spectrum, I have to limit the exposure so it doesn't saturate. But at the blue end of the spectrum, especially when the blue star is gone, I mean, the signal level is really low. And so for most nights, if I had to use about a 15-second maximum exposure to avoid saturating the blue end, but I needed to accumulate an hour of total exposure to get the signal to noise ratio up at the red end. So it'd take 2 hours of 15-second exposures stacked on each other. And of course, these modern CMOS cameras, it's like what, 20, 30, 40 megs per image. I was getting, gigabytes per night. The other thing that happened is because I was trying to use the longest sub-exposure possible. There was one night where I lost half the night because for whatever reason, when I started, the seeing was really poor. And so I think I was able to go up to like a 20 or 25-second exposure that night. And then after a couple of hours, the seeing settled down, got great. The star shrunk. All of its light was going through the slit, and it was all overexposed.
Life is tough.
Yeah. Well, yeah. And by the way, on a somewhat different subject, T Corona Borealis. Gary Walker pointed out to us recently that when it goes pop, it's going to go from 10th magnitude to 2nd magnitude, potentially in just a few hours. And if you happen to be the one who's watching it at that moment, so we're all moved to where I'm taking on T-Core Bore 10-minute exposures. Well, I take one 10-minute, one 1-minute, and one 15-second exposure, and then another 10-minute and a 1-minute and a 5. So if it does go pop, at least I'll have data on it.
That's a great paper, Bob. I really enjoyed the things, particularly where you took the differences between the reference spectra and then was able to show a predicted minus your observed. That was a good trick. One thing you might think about doing is if you can arrange it with your mount, and you should be able to do this with the Paramount, is something called slit sliding. And that's where you put the star on the slit and you just let it slide along the slit at a known rate. And that accommodates anything from, that way you could catch the rise time on that T-core bore pop.
Oh. Yeah, I can understand that. Oh, by the way, one of the things that we sort of take for granted now, that translation of the stellar spectrum into a transmission function by adding and dividing spectra. Imagine doing that if your spectrum was on a glass photographic plate. You know, we take for granted that we can manipulate our spectra and photometry mathematically. It is a gigantic thing, you know, back in the 60s and even the 90s to try to do the equivalent. That's what they did. And you've got to recognize the non-linearity of the photographic. Oh, we live in a wonderful time. Okay, is my time up? That means I get to bring the meeting to an end. That concludes our final presentations for SAS 2024. So thank you to the SAS Board and Program Committee. Thank you especially to John and Bob for keeping the screen lit throughout the last 3 days. Well done, guys. And to Jerry for being moderator and Bob Stevens for being photographer. We'll share the photos in due course. And there wouldn't be an SAS without our dedicated observers and those of you who give us talks. So thank you all for making this last 3 days a busy, educational, entertaining, and provocative time. Thank you to our sponsors for their generosity and helping us be able to put on a session like this every year. Don't forget about Rachel's in-star session tomorrow at 9 o'clock in Hunter's Peak if you're interested in that kind of thing. 2 days of technical talks focused on small telescope science. And we've heard the full breadth of what we talked about last night on the role of small telescopes across the universe and across modes of observation. I should have had the Monsignor drop in and give us a homily here on the Epistle of St. James, where he says, "You've heard, don't just listen, but be prepared to act on what you have heard. The one who acts and perseveres will be blessed in his endeavors." So go home, observe, come back next year and tell us what you saw. Or as Brian Warner would say, do something with that telescope. Thank you all. Have a good time in the evening reception.